So today we are going to be wrapping up our discussion on flow past objects. I'm going to do a quick review on the packed bed, then we're going to talk about fluidized beds and how they differ from what we see in packed bed flow. So from last time, what color would you guys like? Do you have any preference?
Blue.
You like blue? Light blue or dark blue?
Light blue.
Oh.
Do I have anybody else wants to say a vote?
Black.
Traditionalist. How about I'll use black and blue. So last time we talked about packed beds, and for a given system, where we have a packed bed obstructing our flow, we know that we have a greater pressure drop in our packed bed as compared to unobstructed flow. And to quantify that frictional dissipation, we can use the Argon equation, which can be written like this. (1.75) velocity squared times our length, 1 minus epsilon over our sphericity times the diameter of particle times our void fraction cubed. And in this we find that we have two portions in our system. We have a laminar flow portion and a turbulent flow portion, which, if we can identify systems where our Reynolds number is sufficiently small or less than 1, I shouldn't have to say much less than 1, less than 1's fine enough, we can use what's known as the Blake-Cosney equation, which allows us to approximate our pressure drop as simply that first term, U naught, viscosity, L, 1 minus epsilon squared over rho, sphericity squared, particle squared, times epsilon cubed. So only the first term is important. And if we have a higher Reynolds number that's considered fully turbulent, which is greater than 1,000, we can use the Burke-Plummer approximation, which tells us for the system, we can calculate our pressure drop by the second term, which can be written here. It's epsilon cubed. And so these problems can be solved one of two ways. Given a system, you can just use the Argon equation, or if you'd like, you can first calculate your Reynolds number, which is equal to rho U naught d over 1 minus epsilon mu, and then decide if it's laminar. Here I said I would use two colors to confuse everybody. Or transition. And then based on that, you can either use the Argon equation or you can use one of the approximations, the Burke-Plummer or the Blake-Cosney equation. And then from there, you can calculate delta P or F using your Argon equation the Blake-Cosney or the Burke-Plummer. And I think we worked an example problem associated with these at the end of last time, where we looked at a system, went ahead and used the full ergon equation, solved for each term, and based on that, we found that the laminar flow portion provided essentially the majority of our expected frictional dissipation, and so the flow is most likely in the laminar regime. All right. Any questions over packed bed flow?
One quick question. Whenever we have delta P over rho, is delta P PI minus PO or PO minus PI?
It would be PO minus PI, or pressure out minus pressure in. All right, now we're going to talk about fluidized beds. So for a packed bed, now let's say I'm going to draw it like this, and I've got flow moving up through our column. And the question that I have is what happens to our pressure drop as you, okay, I don't like the thick, that just seems very too thick. So what happens to pressure drop as I increase my flow velocity?
The pressure drop should increase.
Yeah, I was going to say the same because most of the equations have velocity directly proportional to pressure drop.
All right, perfect, right? So the answer should be, that my pressure drop should increase. What happens to the length of the packed bed?
It will increase because air will, or whatever fluid will get in between the particles, and it'll cause the particles to rise.
It can, but if I'm considering a packed bed, I would typically state that my bed length will remain constant. And I'll explain why here in a second. And so that's for a packed bed. Now, if my flow rate / flow velocity is high enough, here I'm going to have to do this because I keep clicking into other lecture days. Something interesting happens, such that if I looked at a particle in my bed, I could ask myself what forces are being acted upon the particle. So what forces do you think that are happening?
Drag.
We have drag force. Which direction is drag force happening on our particle?
There's some gravity working on it.
All right, so we've got drag force. I know gravity is down. Which direction is gravity?
Assuming the particle is moving from left to right, the drag force would move in the left direction.
Well, it's not moving anywhere, but the fluid is moving from the bottom up. Do you see that here?
Yeah.
So if the fluid's moving upwards through the bed, which direction is the drag force being exerted on our particle?
It's force of drag is pointing up.
All right, the force of drag is pointing up. And we have one more force that, albeit very minor, and that's our buoyant force. So if I was going to do, my famous force momentum balance, I would say drag force minus buoyant force minus gravity equals 0, right? Where if I was going to look at the force due to gravity, I would have some form of, I find that the drag force equals the buoyant force plus the force due to gravity. Or the drag force is equal to some relative density, right, times the volume of the particle times gravity. Something associated like that, right? I'll make this if it's a sphere.
Why is the buoyant force pointing down?
No, you're right, it is pointing up. Thank you. Doesn't change my math, but something associated with that. I don't know. I don't want to assume it's some volume of the particle, relative density, gravity is involved, right? And so
I feel like it should change your math because it shouldn't force of drag plus the buoyant force equal force of gravity.
I'll fix my math then. Thank you for that. Okay. So you're right, it does. And so what you end up with is force of gravity minus buoyant force. That's where this term shows up. So I had already accounted for it in my third equation, just not in the first two. And so which of these terms is going to change with increasing flow rate? Is the left-hand side or the right-hand side going to change with increasing flow rate?
Drag.
All right, so our drag. So we say our drag force increases. And so there comes a point when the drag force equals the force due to gravity, or the relative force due to gravity accounting for buoyant force. And at that point, where I say when FD is equal to, we essentially get a weightless particle in our bed. And any velocity above that is considered what's known as a fluidized bed. Because we see that essentially the drag force being exerted on the particles by the fluid has overcome the gravitational forces keeping the packed bed in place. And so with that force essentially being canceled out, the particles exist in a fluid-like state, which we consider a fluidized bed. And a good illustration of this is what I see here in the notes that I provided, that once you get to a fluidized bed, we start to see an increase in our bed length as a function of velocity. However, one thing that's interesting is that our pressure drop in a fluidized bed is very minimal. And that can be, kind of described here, where if on this left portion, this is the packed bed, and in this right section, we have a fluidized bed. The x-axis is a dimensionless velocity. The y-axis is both a dimensionless analysis of pressure drop here, as well as bed height on the left side. And so for a packed bed, we find that increasing the velocity constitutes an increase in the pressure drop. But once you become a fluidized bed, the expected increase in the pressure drop is very minimal. And instead, what you see is once you have a fluidized bed, we see a proportional increase in our bed length. And so we start to expand the bed rather than gain a greater pressure drop, because at that point, the fluid is literally being able to push the particles out of the way and not necessarily having to lose a whole lot of pressure energy because of it. Now, if you go too high, what you end up with is essentially washout, where you don't have a bed anymore, you just have stuff and a headache downstream. Any questions on that? And so how we describe fluidized bed or pressure drop, we don't really worry too much about pressure drop. What a lot of times we're interested in is knowing the minimum fluidization velocity.
You're still on the PowerPoint.
Thank you. And for a given system, we find that our minimum fluidization velocity is a direct function of combining our ergon equation with what we see in our momentum balance expression. And we end up with an expression that looks like this: G times rho of the particle minus density equals 150 mu naught U sub m times 1 minus epsilon divided by sphericity squared, diameter of the particle squared, times epsilon cubed, plus 1.75 times our density times our velocity squared, divided by sphericity times the diameter of the particle times epsilon cubed. And so what we can see in this system is that, we see the same kind of relationships associated with a laminar portion of flow. So we have our laminar flow portion, our turbulent flow. And this is kind of that, looking at that relative.
What is the velocity of M?
This one actually has different numbers.
What?
What is the velocity of M?
That just stands for the minimum fluidization velocity. So it's like U min. And I'll make that really clear here. U sub M. And so if I'm interested for a given packed bed, trying to identify the minimum fluidization velocity, I can use this expression here. What we kind of begin to see, though, is that if I look at this system, what I end up with is some number equal to another number times our velocity plus another number times our velocity squared. And so what this should tell you is, in order to solve this, you end up having to put it in this form. Or, it's an A times UM squared plus, I should probably write it like that, right? A times UM squared plus B times UM plus C equals 0. And so what that should tell you is that solving for your minimum fluidization velocity results in a quadratic equation that must be solved. So it results in a quadratic equation. All right, and for this equation, you typically end up with one root. That makes sense. And one root that's negative. And so your solution is going to be the root that is a positive value. So let's look at an example of this. So let's say we have catalyst pellets, about 0.2 inches in diameter, are to be fluidized with 75,000 pounds per hour of air at 1 atmosphere and 75 degrees in a vertical vessel. If the density of the particles are 60 pounds per cubic feet with a sphericity of 0.6, what is the vessel diameter if we assume the airflow rate is just sufficient to fluidize the pellets, assuming a void fraction of 0.45 and a fluid viscosity of 8.8 times 10 to the minus 6 pound mass per foot second. All right. So let's look at this example of a fluidized bed. If you want, I can draw us a problem. Everybody loves practicing their art skills, right? Just me. What was given in the problem? We know our mass flow rate is 75,000 pounds per hour. We know the diameter of the particles are 0.2 inches. Which, if I put that into feet, because it will be more useful, I should get up a very small number, 0.0167 feet. I stated that the pressure is 1 atmosphere. The temperature is 75 degrees Fahrenheit. The density of the particles are 60 pound mass per cubic feet. The sphericity of the particles was 0.6. The void fraction provided was approximately 0.45, and the viscosity was 8.8 times 10 to the minus 6 pound mass per foot second. So what I need to do is look at our expression that we have for our fluidization velocity, figure out what we need to identify. Which I will write out. I feel like I'm missing a term somewhere. Let me take a look. Missing a density. Here. So which values do I have and what values do I need?
You're gonna need to find velocity.
Well, that's true, but do I need any other terms in the system?
Your density of your fluid.
All right, so I need the density of the fluid, right? So I know that based on the conditions, I have 1 atmosphere and 75 degrees F. So I have 14.7 psi, 29 pounds per pound mole over 10.73 psi cubic feet per pound mole, degree Rankine. And I have 75 degrees, which in Rankine is approximately 535. So if I solve for the density, Let's see what I get. About 0.074 pound mass per cubic foot. So with that in mind, I can plug in all my values and identify a reasonable solution. Let's see what I get. So gravity is 32.2 feet per second squared times the density of the particle, which is 60 pound mass per cubic foot, minus the air density, 0.074 pound mass per cubic foot. So I'm just going to solve for this one term at a time. So if I solve for this, I end up with 1,930 with units of pound mass per foot squared, second squared. So I look at my next term, which is 150 times my viscosity, which was given as 8.8 times 10 to the minus 4, I believe, 6 pound mass per foot second times our 1 minus our void fraction of 0.45 divided by our sphericity squared, or 0.6 squared, times the diameter of our particle, which we found was 0.0167 feet squared, times our void fraction of 0.45 cubed, times u sub m, which is what we do not know. So what does this term come out to be? I ended up with 79.35. Let's look at our units. Let's see, we have pound mass per foot second on top, and we have feet squared on bottom. So I see pound mass per feet cubed second squared. Second times u sub m. Now u sub m is in feet per second. So if I look at the product of this, I end up with pound mass per feet squared second squared. Which is the same units as the term that I have above. Everyone following along all right? I'm going slow because it's a lot of math in these types of problems. All right, now we have our second term, so we need our last term. So our last term is 1.75 times our density of our fluid, which we ended up with 0.074 pound mass per cubic feet, divided by our sphericity, 0.6, divided by our diameter particle, 0.0167 feet, divided by our void fraction cubed, times our velocity squared. We can double check that. Doing this calculation, I ended up with approximately 141.8. Looking at our units once again, I end up with pound mass per feet to the fourth times um squared, which if I looked at these two combined, that gives me units of pound mass per feet squared second squared. I'm doing this check because it's important to make sure that you're doing the calculations correctly, as well as keeping track of how well these numbers fit together. Because you can't put it together if there's an error or mistake such that the units don't match up. And so luckily they all do. And so what I can do is I can put this in a form that's a quadratic equation. And I can say 141.8 times u sub m squared plus 79.35 times u sub m minus 1,930 equals 0. So if I put this into a quadratic equation solver, because it's 2020 and you're not in algebra having to do it by hand, you end up with 2 roots. So you get UM is equal to negative 3.97 feet per second, or 3.42 feet per second. Pick the root that makes sense. So now we know what our velocity is. And in order to find our diameter, we can say if that's our minimum fluidization velocity, and given our mass flow rate is 75,000 pounds per hour, we can solve for our volumetric flow rate by taking our mass flow rate divided by the density of our fluid, or I can say 75,000 pounds per hour divided by 0.074 pound mass per cubic feet, and then convert this. 1 hour is 3,600 seconds. I should get my volumetric flow rate. Which I get approximately 281.5. Cubic feet per second. Quite a bit of flow. And then, knowing my volumetric flow rate, I can say, well, if my volumetric flow rate is my velocity times my area, which is my velocity times pi times our diameter squared over 4, that tells me if I want to solve for my diameter, I just need 4 times my volumetric flow rate divided by pi times my mean velocity, now to the square root. So since I need to solve for my diameter, I can say it's the square root of 4 times 281.5 cubic feet per second divided by pi divided by the velocity we found of 3.42 feet per second. So if I look what I have under the radical, I end up with feet squared. So the square root of feet squared is simply feet. So if I do this math, I end up with approximately 10.2 feet for my required diameter. Anything beyond that, it will exist as a packed bed. Anything below that, our superficial velocity will be much higher. So you'll either end up as a highly fluidized bed or could run the risk of washout. Any questions on this example or the discussion of fluidized beds? Last couple of things I will say before we end for the day. I strongly recommend you look through towards the end of the chapter on this section of fluidization, about pages 180 through 180, essentially 185, because there are a few other equations that you may need for homework. One being looking at the expansion beds, or fluidized beds, excuse me, where we see that if you're looking for a bed expansion length as a function of the bed at the minimum fluidization velocity, L sub m, we can quantify it times the void fraction at fluidization over the current void fraction. This being equation 757 on page 182. All right, that's all I have for today. That kind of concludes our discussion on fluidized bed. Most often than not, we're interested in finding that minimum fluidization velocity to identify if we want to operate as a fluidized bed, what's the design specifications or just processing conditions associated with our flow rate that's necessary to have our system exist as a fluidized bed. All right, guys. Well then, take care. Have a great weekend.
Thank you so much.
No problem. Have a great weekend, guys.